Hi, my name is Girish and I'll present our work on generating robust parallel programs by modeling non-determinism. Albert Einstein once said, "Insanity is doing the same thing over and over again and expecting different results." However, computers can do the same thing over and over again while putting out different results every time. Then are computers insane? Well, regardless of using computers to do sane or insane things, they are non-deterministic. Non-determinism is characterized by different execution behaviors like timing, memory states, etc., exhibited during repeated execution of an application with the same inputs under similar execution environments. This difference in the behavior is caused by several factors such as the underlying architecture, OS, the runtime, etc. In sequential programs, non-determinism is induced by the co-executing programs, OS context switches, architectural factors such as branch mispredictions, cache misses, TLB misses, etc. In addition to these factors, parallel programs are also affected by interference, resource sharing, and scheduling decisions among the threads. For example, as shown in this figure, two threads of a program can execute a code in different orders during different runs because of non-determinism. Parallel programs can have very rare race conditions caused by rare thread interleavings that are not exhibited during testing and sneak into production. When they are found in the open, developers have a very hard task even just reproducing it. For example, a concurrency bug in parallel bzip2 took 4 months to fix because of the difficulty in reproducing it. These rare interleavings are very non-deterministic. Non-determinism causes different thread interleavings in parallel programs. Hence, influencing non-determinism affects these rare interleavings. Can we have a control on non-determinism to make parallel programs robust? Robust programs are the ones that have very few failures due to bugs. Decreasing non-determinism in production or released programs will reduce the rare thread interleavings and the likelihood of a rare bug manifesting at runtime, since testing covers most of the likely and commonly occurring thread behaviors. On the other hand, increasing non-determinism helps developers reproduce rare bugs easily by exercising corner case interleavings. Prior works have tried to remove non-determinism completely, but this affects performance very severely and may not be a practicable solution towards debugging, since debug time goes up significantly. Conventionally, developers have switched compiler optimization levels for release and for debugging purposes. In the debug cycle, certain optimizations are suppressed and such versions are then used for parallel debugging. However, how do compiler optimizations affect non-determinism, which in turn affects thread interleaving and debugging, is not known. So in order to answer this question, we must first find models for non-determinism and then be able to correlate these to compiler optimizations. In this work, we quantify and characterize non-determinism due to the architectural factors such as cache misses, branch mispredictions, etc. using performance counters while minimizing the effects from the OS. We build a non-determinism model on a per program basis. We use the model to predict the compiler optimization level corresponding to the maximum and minimum non-determinism. We finally use these predicted optimization levels to select the debug or production version of the application. We empirically establish that the correlation between the model predicted compiler optimization level and non-determinism is highly accurate. To develop the non-determinism model, we define some new terms. First, commit order is the order in which the threads complete a code section or reach a barrier. For example, in the case of 4 threads, 2134 is a commit order in which thread 2 commits at position 0, thread 1 commits at position 1, 3 commits at position 2, and 4 commits at position 3. Similarly, 4321 is another commit order. Totally, such n factorial commit orders are possible. However, not all of the n factorial commit orders are expressed even when the application is run more than twice n factorial number of times. Each unique commit order brings out a different behavior. If we define non-determinism as the various behaviors seen at a synchronization or commit point, then we can quantify non-determinism as the total unique commit orders seen during repeated runs. More the number of unique commit orders or permutations, more the non-determinism. If a program always expressed or committed in one permutation, for example 2, 1, 3, 4, then the program would be a deterministic parallel program. We define the most frequent commit order seen during repeated runs as the most common permutation, MCP. The commit distance of a thread in a permutation is the distance of its commit from its usual commit in the MCP. For example, if the most common permutation is 2, 3, 1, 4, then the commit distance for thread 1 in permutation 1, 2, 3, 4 is 2, since it committed in position 0, which is 2 positions far from that in the MCP. Architectural factors are the artifacts of the architectural causes of non-determinism, such as cache misses, branch mispredictions, etc. These artifacts are measured using performance counters. We model the commit distance in terms of the change in these artifacts. A thread commits at a different position due to its timing variation from its position in the MCP. We contend that this timing variance is contributed by various artifacts such as cache misses, branch mispredicts, etc. Thus, commit distance is proportional to timing variance, which in turn is proportional to the function of hardware performance counter deviations. This figure of commit distance versus timing delta of a thread in Canniel benchmark empirically shows that the commit distance is proportional to the timing variance. In the figure, y-axis is the commit distance and x-axis is the delta in time. This slide presents the overall picture of our framework. We first instrument a version of the application and collect the hardware counters by profiling it. We then use the collected hardware counters to generate a model for non-determinism. The polished model is then used with the hardware counter information generated from other versions of the application to predict the most and least non-deterministic version of the application compiled by the corresponding optimization levels. For generating the model for a given application, we profile the hardware counters per thread. We do get several readings for any commit order. We then average the values for each thread belonging to a commit order. We get the deviation of the average counter values from that of the average counter values of the thread in the MCP. This gives us the deviation of the architectural artifacts from the normal most common behavior. We learn the relation between the commit distance and the delta in the hardware artifacts as a linear model. Linear regression because the relation between the commit distance and the execution time is linear, as we saw earlier. We use R to learn the linear regression model using small and medium inputs for training and then use large inputs for testing. Since small and medium inputs give different range of artifact values, we normalize them over the most common permutation values for each input. We generate a linear model using the hardware counter and commit distance values for every 500 runs using O0 version of the program. We depend on adjusted R-squared value of the model for convergence. Adjusted R-squared is a measure of how close the model is to the actual data. If the adjusted R-squared value of the new model is higher than the previous iteration model, then we use the new model. We stop once the model stabilizes for at least 4 consecutive iterations. We use the drop term test from a library called mass in R to remove non-influential architectural factors in the model. Once we have the final model, we run O0, O1, O2 and O3 versions at step size of 500 runs and collect the hardware counter values. We plug the values in the model and sum up the absolute values of the model for each thread. We need a stopping condition that exercises the model adequate number of times. If we stop early, then the correlation between optimization levels and non-determinism will not be captured. On the other hand, repeating this for very large number of times is very time consuming. We decided to use Bollinger Bands as a stopping condition for predictions. Bollinger Bands are used to measure the stability or convergence of a financial entity. We use it to gauge the stability of the prediction of the model. For every iteration of 500 runs, we generate the 6 Bollinger values for each version of the program. Once the majority of the Bollinger values, that is 4 out of 6 values, are either minimum or maximum for 4 consecutive iterations, we stop. The minimum value corresponds to the least non-deterministic version and the max value to the most non-deterministic version. We verify the accuracy of the model by running every version for 80,000 runs and recording its non-determinism in terms of the unique commit orders that are exhibited. We run our experiments on an 8-core Intel Xeon machine with hyperthreading disabled. We run Linux on the machine. We pin all the threads to minimize the interference from the OS. We compile the programs using GCC 4.7. We evaluate our framework on pthread programs in Parsec benchmark suite. On all these benchmarks, we observed that the MCP is a common trait. We validated the model by running each version of the program for 80,000 runs. The model predicted the least non-deterministic optimization level correctly in all benchmarks except Fluid Animate. In Fluid Animate, the model predicted the next least non-deterministic version, which has 6 more permutations than the actual least non-deterministic version, which has 11,843 permutations in total. The least non-deterministic version reduced non-determinism up to 80%. The model is not as accurate when predicting the most non-deterministic version. It is right in 3 cases and is close in 3 others, except Fluid Animate, which has 38% fewer unique permutations in the predicted version compared to the actual most non-deterministic version. On average, the model converges on 4,300 runs during model generation. Compared to 8 factorial, which is 40,320 runs, 4,300 runs, which is equal to 10%, is low. The number of runs for prediction vary but converge faster than training, except for Caniel benchmark, which takes around 8.2 hours. Compared to developers spending days to fix a bug, 8.2 hours is a small time given away to making programs more robust. In the model for each of the 8 threads in body track benchmark shown here, the commit distance, in turn non-determinism, is affected in all threads by H14, conditional branch instructions, H5, L3 cache misses, H6, L3 load misses, H1, L1 data cache misses, H4, L2 cache misses, H7, data TLB misses, H13, unconditional branch instructions, H12, L2 store misses, H15, conditional branches taken. This figure shows the summary of the architectural artifacts that play an important role in the corresponding models. Overall, it can be easily seen that the non-deterministic predictions for branches, the fluctuating access time for memory during cache and TLB misses, disturb applications, inducing more non-determinism. Also, resource crunch and some special functional units such as floating point units can influence non-determinism in applications. We plot the difference in the number of behaviors covered by the top 25 permutations of the predicted most and least non-deterministic optimization levels. As we can see in the figures, the top 25 permutations in the most non-deterministic version cover much fewer runs compared to the least non-deterministic versions. We define coverage as the total percentage of the 80,000 runs covered by a given number of permutations, and in this case, the top 1000 permutations. Higher coverage implies repeated runs will exhibit the top tested permutations, which is a way to describe the robustness of the released program against erratic behavior. We compared the coverage for the actual most non-deterministic optimization with the coverage of the optimization chosen by the model as least non-deterministic. As shown in the figure, the coverage is improved in all the benchmarks, the highest improvement being 66.48% in body track. The model picked optimization for least non-deterministic version can be O0, which can be very slow. So to reduce the performance degradation, we isolate the critical section in question and compile it with the predicted optimization level separately and the rest of the benchmark with default optimization level separately. We can see from the figure that we are better than sequential and close to the default optimization level. Stream cluster has a known race condition which is caused by a missing barrier in parsec version 2.1. Our model predicted least non-deterministic version did not hit the race condition during 100k runs. We also inserted 10 random race conditions in Black-Scholes and Swaptions. In 80,000 runs, the predicted most non-deterministic version in Black-Scholes hit 6 of those conditions and failed 11 times, and the least non-deterministic version failed only once. In case of Swaptions, the debug version hit 7 conditions, whereas the release version hit 5. The debug version also failed 7 times on a particular bug, whereas it failed only once in the least non-deterministic version. One of our previous work, DSTM, deterministic STM, has sacrificed performance for deterministic execution, but it allows a developer to systematically replay different permutations in a highly efficient manner for STMs to drastically improve debugging time, and in fact has exposed 2 extremely difficult to find bugs in the highly used STAMP benchmark suite. As against this, current work focuses on increasing or decreasing non-determinism to expose or suppress rare thread interleavings, to debug corner cases, or to make programs robust. Another work in CGO 2019 from our group modeled non-determinism in software transactional memory to reduce timing variance, which makes STMs very useful for game and other soft real-time applications. While that work targeted timing variance, this work targets program robustness in terms of fewer failures due to bugs. In future, we would like to look at other definitions of non-determinism. In this work, we only looked at different commit permutations to define non-determinism. We would like to model other sources of non-determinism such as OS, runtimes, etc. We would also like to devise compiler optimizations that are geared towards non-determinism. We would also like to explore debugging methodologies by actively controlling non-determinism. To summarize, we developed a systematic methodology for quantifying and modeling non-determinism and showed how we can use the model to predict most and least non-deterministic optimization levels. The most non-deterministic version with increased permutations can easily help developers reproduce bugs. The predicted least non-deterministic version reduced non-determinism by up to 80.23% compared to the most non-deterministic version. And the coverage increased by up to 66.48%. We also showed how some of the bugs are made benign in the least non-deterministic version. That's all from me. I'm happy to answer any questions.